All right. So the last thing I have to cover is the last two slides, which I titled Calculus of Inverse Functions. I'm going to explain that right now. All right. If you remember back to Unit 1, an inverse function can be obtained by reflecting the original function's graph over the line y equals x. Do you remember that?
Yeah, that makes sense.
Okay. And we said this before, we can obtain the inverse function with algebra by switching the x's and y's in our equation.
Okay, yeah.
All right. Additionally, if we turn our function into its inverse, the slope at that point, or the derivative at that point, will change. Let's look at Jamboard, or let's go into Desmos actually to illustrate it. All right. I'm going to graph the function x squared. And its inverse function is, so if this function is y equals x squared, then its inverse function
x equals y squared?
Yep, exactly.
Cool.
All right. So here's the derivative. So here is a point with the same x coordinate, right?
Yeah.
But notice how they have different slopes at that point. So the inverse function, and by the way, this is not a function, right? So we can turn it into a function by just making it the y equals the square root of x. You see how that's the same as x equals y squared? We take
this. It's the same thing. It just has the right.
Yeah. Because the reason this has two of them is because when we take the square root of this side, we have to do plus or minus.
Yeah. Okay.
But that makes it not a function. So I'm just going to write y equals the square root of x, which will do one side of it, which is oh wait, this is actually a perfect reminder of what we talked about in Unit 1. Remember how we said that if a function is not one-to-one, meaning an output has many inputs associated, or more than one input associated with it, it won't have an inverse?
Yeah.
Well, when we took the inverse of the function, what do we get?
Not a function.
Exactly. And is that because x squared is not one-to-one?
Yeah, it's because there's multiple x
Yep.
input.
Yeah, exactly. And we can think about it. Yeah, we can think about it back to our original example. If the inverse takes in outputs and spits out inputs again, if it took in 2, it would spit out 2 inputs.
Yeah.
So the function itself is taking in one thing and spitting out 2 answers. So it's not a function.
Okay.
So I'm just going to make it a function by ignoring the other side and just doing the square root of x.
Sounds good.
Oh. All right. So you'll notice that this function is the inverse of this function. If we just look at this side. All right. As in, if we took the square root of x squared, we would just get x. So you can clearly see how these functions undo each other.
Yeah, definitely.
So they're inverses, but if you look at x equals 1, their slopes are different. And there's a relationship between their slopes. The slope of the inverse function is 1 over the slope of the original function. And I'll explain why with Jamboard. All right. You'd agree that the slope of our original function is a tiny change in the output divided by a tiny change in the input, dy dx.
Yeah.
But with our inverses, the outputs and inputs have switched. So a tiny change in the output is dx divided by a tiny change in the input is dy. Right?
Yeah.
So do you see how the slopes are then going to be reciprocals?
Yeah, I see that.
Because they're the same except, so here's what I'll do. I'll say if this is m, then dy over dx equals 1 divided by m.
That makes sense.
Cool. And that's why. If our inputs and outputs have changed, then the derivative will be the opposite fraction.
Okay, cool, yeah.
So if I knew that my derivative of x squared at x equals 2 is 4, then the derivative of the square root of x.
Of x would be 1 over 4?
Exactly.
Okay, cool.
All right.
That makes sense.
And so that makes sense, right? All right. So that's what we would predict. That's what we would predict would happen, right? And all math and science is going like, I'm making a prediction with math about what would happen, and let's see if it's true. So we made a prediction, and we're going to see if it's true. All right. So the derivative of the square root of x is 1 over 2 times the square root of x. So when x equals 4, we get 1 over 2 times 2, which is 4. 1 over 4.
Let's go.
So the prediction we made is correct. And we expect it to be, right? So yeah. I like doing these examples because it shows how we're gonna learn the power rule for square roots in a bit, or tomorrow. So I think it's cool. Tomorrow we can see how the idea of inverse functions and the power rule, they agree with each other, as math should. If math is to make sense, we should be able to approach a problem in 2 different ways, and if both methods are valid, we should get the same answer. And we do.
Yeah.
Awesome. So yeah, the slope of the inverse function at a point is just 1 over the function, 1 over the slope of the original function. Oh, I'm at the wrong slideshow. I'm just going to delete this because we're not using it anymore. All right, so we covered that. All right, so let's look. This is a theorem. This is the last theorem we're going to learn today, but we're going to try and tickle it out. We're not going to look at it. We're going to try and discover it ourselves because I think it's cool to discover it ourselves.
Sounds good.
All right, so I'm going to draw a function. All right, here's a little trick question. What can you tell me about the derivative at this point?
Does it not exist?
It doesn't exist.
It's different from both sides.
Exactly. So when we find the inverse, right, our function is going to look like a reflection over y equals x. So we're going to get this. Is the derivative at the new point defined?
No.
Yep, doesn't exist.
So if it's not defined on one point, then it will not be defined on its inverse?
Yes, but there's one exception to that rule. I'm going to get to that in a second. All right.
Okay.
What I want you familiar with is the idea. So remember we said that if there's a corner we call this a cusp because it kind of looks like a curvy corner. The function that won't have a derivative there.
Okay.
So if the original function has a cusp or a corner, it's clear to see that the inverse will also have that same cusp or corner.
Yeah.
So then the derivative there will also be undefined.
Yeah.
Additionally, if I found the inverse function, well, first of all, it won't be an inverse function, but if I found the inverse of, why am I not just going to the next slide? If I found the inverse of y equals 4, I'd take the line y equals 4 and I'd reflect it over the line y equals x, right?
Uh-huh.
What happens when I reflect this line over y equals x?
That's just x equals 4. It's like a vertical line.
Exactly. So taking this idea into any function, if the derivative of some function is 0 at a point, what is the derivative of its inverse going to be at that point?
Also 0? Yeah, also 0.
You're very close. You're very close.
Or is it undefined?
Yes.
Because it's just a vertical line.
Yep. Here's another way. Remember we said that the slope of the inverse is 1 over the original slope?
Yeah, so then that's 1 over 0, which is undefined.
Yep. So do you see how if we have our derivative equal to 0, the derivative of our inverse will be undefined?
Okay, cool. That's perfect.
Cool. Awesome. But if we had if we had our derivative undefined, for example, here's the graph of the square root of x, and the cube root of x. This is the graph of the cube root of x. What can you tell me about the derivative here?
Wait, sorry, ask it again.
No worries. So here's the graph of y equals the cube root of x. All right. And it looks like this. What can you tell me about the slope or the derivative at this point? Does it exist?
Potentially, but it's super, super close to vertical. So does it not exist?
So at one point specifically, I'll show you by drawing the cube root of x. The slope is vertical. It's only at one point, but it becomes vertical. You see, at points close to it, it gets steeper and steeper and steeper.
Oh yeah, I remember.
But at the specific point itself, it's vertical.
Yep.
So the slope is undefined here. But would you agree that the inverse of the cube root of x is x cubed? Because they undo each other?
Yeah,
what about...
So then at 0, 0...
What's the slope of x squared, or x cubed?
0.
Exactly. So it's possible for our original function to have an undefined derivative, and our inverse to have a perfectly normal derivative.
Okay, yep.
But that's only when there's a vertical tangent.
Yeah.
All right. All right. So with that, we've kind of snuffled out the theorem, and we can go straight to it. All right. So the theorem says, if a function is differentiable on some interval, all right, some interval I, and I hate how they write this, so I'm just going to rewrite it over here. Let's say the interval I is just between 2 points, A and B, including A and including B. All right?
Okay.
So the theorem says if f is differentiable at every point on I, all right, meaning you can find the derivative at every point between x equals A and x equals B.
Okay, yes.
Yep. And the derivative is never 0.
Uh-huh.
All right? Because remember we said if the derivative is 0, the inverse will have an undefined slope.
Yeah.
All right? That means that the inverse is differentiable at every point on the interval f of I. And the reason we say f of I is because remember the inverse function takes outputs of the original function as inputs. So the inputs of the inverse, would be f of A, right, to f of B.
Yep.
Does that make sense?
That does make sense.
So the reason they write it's differentiable on f of I, it's because the interval x equals A to x equals B, if we're considering it from the inverse function, that interval is f of A to f of B, because the inverse takes in outputs of the original function.
Okay, yeah.
Cool?
Yeah.
So that's what this theorem's saying. And it's what we kind of elucidated before. If f is differentiable at every point on an interval, meaning you can find its derivative, and it's never 0, then we know we can find the derivative of the inverse function by taking 1 over that derivative. So as long as it's never 0, and as long as the original function has a derivative at every point, we can find the derivative of our inverse at every single point as well.
Okay, yep.
So then f of negative x would be differentiable on the interval f of I, meaning we go from f of A to f of B. Because, yet again, it's no longer x equals A to x equals B, because our inverse doesn't have x as inputs, but rather f of x. So it's from f of A to f of B.
Okay.
So that's what this theorem means. So at first you might be like, I have no idea what it's saying, but now that we've gone through it, I hope you at least understand the idea of what it's saying.
Yeah, I think it's pretty self-explanatory. Like, I think it just like makes logical sense. Like, if on one function every point is you can find its derivative. Then if as long as there's no straight part, like as long as every point is differentiable, then it will also be differentiable on its inverse, because there's no like point or spot that like it wouldn't be.
Remember, we said that the 3 times a function will be not differentiable is that there's a corner, a cusp, and a vertical tangent, a vertical line. So if the original function doesn't have any corners or cusps, then the second function won't have any either. So we've eliminated the first 2 just by saying that if the function has to be differentiable on the interval. If it's differentiable on the interval, by definition, it can't have any corners and cusps, because then it would not be differentiable at those points.
That makes sense.
The last one we can avoid by saying the derivative the original function can never be 0 because that would result in a vertical tangent line of the inverse. So just from these two conditions, you can see how we've eliminated the possibility of the 3 instances where the function won't be differentiable. Cool. So that's it. I don't know why I wrote this, but I just said no cusps, no corners, no tangents, no problem.
I like it.
Cool. All right. So that's it for today. I'm going to end the YouTube video. We're going to get into this tomorrow. Thank you guys for watching. I'll see you guys next time. And I hope you guys have a good day. I'll see you guys.